So I'll let you go ahead and start the recording. Let me know when you've got that going. Or
Okay.
Erica. Oh, Erica's got it going. Okay, cool. Welcome, everybody, to NASA's Universe of Learning Informal Network webinars. Today, we're going to be doing Understanding the Electromagnetic Spectrum. How does the universe work? Thank you again for joining us. And if we get to the next slide, we'll see the people who are here with us today. As always, we have Mary DeSalt and Erica Wright from the Smithsonian Astrophysical Observatory. Erica is off camera answering all of your questions in the chat box as we go along. So if you do have questions, please put them in there and she will gladly respond to what is going on, and she'll also make sure we're aware in case you have questions and need us to answer them out loud. Also with us, we've got myself, Tim Rue, and Brandon Lawton, who is, again, lurking behind the scenes, keeping track of what's going on in the chat. He'll chime in as needed as we go along today. And we also have Natalie Wimberly from Smithsonian Affiliates here working with us today. We're quite happy to have her along and help make this all run smoothly. Later today, you'll be meeting Kim Arcand. She is the visualization lead at NASA's Chandra X-ray Observatory and the Smithsonian Astrophysical Observatory. She'll be talking about how we make many of these wonderful things that you see coming out from NASA's Universe of Learning. And you'll all get a chance to be able to ask her some questions as we go along as well. So today is the third in our series of 7 webinars. We're continuing every other week. This is the second part of How Does the Universe Work? And we'll talk about next week once we get to the end of it, but that's where we are in the grand scheme of things. Today, we'll be touching a lot on how do we know, how do we actually figure out what there is out there in the universe, and we'll be talking a little bit about the structure and makeup of the universe, these different parts of light. So we'll start off. Mary will talk about the connection to the resources. I will talk a little bit about what is light and what we can learn with it. Kim will step in and we'll talk a little bit about coloring the universe. We'll have some question time for her and we'll have next steps. As always, please ask questions throughout. You can do it through the chat. You can pop on and say something out loud. We're happy to have that discussion. If we can get some discussion going as we're going along here rather than just us talking at you, that would be great. And I want to make one other announcement. You guys may have heard about the National Emergency Test Alert today. That's happening in about 14 minutes while we're in the middle of this webinar. So when all your phones go off and mine goes off and everyone, that's what's going on. So I think I'm going to pass it over to Mary to talk a little bit about the resources we've got.
Okay, thanks, Tim, and thanks for bringing that up. That's great. So we're going to talk about the resources listed on the screen here, and actually I'm going to stop my share for a moment and share again with computer sound, because one of my resources might have sound. So there we go. All right. So these are all resources from Universe of Learning related to the topic of the electromagnetic spectrum and seeing the universe in a different light. And the first resource is ViewSpace, which is the you're sharing the wrong screen. I'm sharing the wrong screen. Oh, nobody wants. Okay. Okay. Wrong screen. Thank you. Share. Step 2. Good sound. Try that. Am I now on the right screen? Yes. Yes. Thank you. ViewSpace. So this media exhibit that's available, in fact, Tim is your main contact person, I believe, for ViewSpace, has content not only from Universe of Learning and NASA Astrophysics, but from other areas of science at NASA. But the video I'm playing right now is a nice little piece from ViewSpace all about the Crab Nebula in different colors of light. And so it's kind of gives you the context for where the Crab Nebula is, and then shows you the view of the Crab Nebula across the spectrum. And one of the things we're going to learn today, oh, I like that. So you actually use a micro observatory image of the Crab Nebula in view space. We'll talk about that resource as well today. One of the key aspects of NASA astrophysics finding out about our universe is that different objects in space glow in different colors or energies of light. And so this is a great little piece on view space about how the Crab Nebula, this is the visible light that shows you the torn apart star that exploded, and that the colors of this filamentary structure are related to the composition. And there's this ethereal blue glow on the inside. Coming from a neutron star, which you can't see in visible light. You actually have to look in different colors of light to see some of the other things in the Crab Nebula. So I'm not actually going to play through this whole clip, but I just wanted to highlight that I think fairly often view space highlights the aspect of multiple wavelengths of light to observe things in the universe, and this is just one example. Another new aspect, in fact, here's the view. I'll just pause it right there. Here's the view of I'm having trouble pausing it. The Crab Nebula that really shows the pulsar at the center of that blown apart star, and you really can only see this by using the an X-ray telescope, Chandra X-ray telescope. So it's really a completely different view than you would get through visible light, and this really helps us understand things. Now, view space also has this new feature of being interactive, and I'm going to bring that website of view space and the interactive element right here. And actually, if I click on it, you can see a galaxy, the Andromeda Galaxy in visible light. And as I slide it over, you can see all those dark dust lanes actually glow in infrared light. And this aspect of view space has, I think, is being developed based on feedback from informal educators, but is really a great tool for highlighting this theme of electromagnetic spectrum. Here's another couple of galaxies in visible light, and again in infrared, all the dust glows. And I don't know if you guys remember, but Brandon as an astrophysicist is dust, so he especially loves these clap, clap, clap. I see Brandon, nice. The next resource I want to tell you about is Aster Pics. We've mentioned this a few times, but one of the things you may not have noticed in Aster Pics is down at the bottom of each image, there's always this color mapping index, which tells you how the colors were assigned to create that image. So this is an image of the galaxy M81 or Messier 81 in infrared, and you can see that although it's a full color image, each color is actually a different wavelength of light we can't even see, a wavelength of infrared light. Here's another image from Aster Pics of that same galaxy, but this time there's an inset from the Chandra X-ray telescope. And so like, once again, there's something you can't see in the blue channel in this image if you didn't have an X-ray telescope. In addition to Aster Pics, the next resource that we wanted to highlight with regard to electromagnetic spectrum and learning about light is Micro Observatory. We've talked about this before. I'm going to just show you that when you request an image from Micro Observatory, if I go to ask for the Andromeda Galaxy, for example, you send your request to the telescope of the field of view. We only have one choice here. Exposure time gives you a hint. It's a long exposure time, but you can choose to apply colored filters. There's a filter wheel in the telescope, just like the Hubble Space Telescope actually has a filter wheel in the Space Telescope. And so you can choose to have 3 observations taken, one through the red, one through the green, one through the blue filter, and use that to make a 3-color image, which I'm going to show you right now how to do. On the Analyze Image tab in Micro Observatory, we have our image processing tool called JS9 4L for learners. It's an astronomical software. Professional astronomers use it, but we've adapted it for learners. And in this tool, you'll see that I have open, I've actually opened 3 lagoon nebulas that I took, or that are actually sample images from Micro Observatory. And so here's the blue image, here's the green, and the red I haven't fully processed yet. I'm going to use the log scale, which enhances dim images. I want you all to try this out because there are tutorials to show you. So again, there's the red, there's the green, and there's the blue. And if you want to type in the chat box, which filter let in the most light, does it seem? There's blue, there's green, and there's red. So while you're typing in the chat box, I'm going to do the processing to create a natural color image to combine the 3 colors of this nebula. So this was the red image. I'm going to tell the computer this was taken through the red filter. Tell the computer this was taken through the green filter. And yes, everyone is noticing that, yes, there's more light coming through the red filter. And then I tell the computer this is taken through the blue filter. And when I know I'm going through this very fast, we are willing to do extra tutorials for those of you who might decide you want to use Micro Observatory with your audiences. I'm going to click on RGB mode, which is going to add the red, green, and blue images together in a single image, in which you start to see that the Lagoon Nebula has this reddish color. It's actually full of glowing nitrogen, which glows in a red color. And this is a natural color image. One thing you notice, the images aren't perfectly aligned. There are tools in this JS9 tool to actually shift the red channel a little bit to the left so they all line up, but I won't go through that at the moment. In addition to taking your own images with Micro Observatory telescopes, we are now just beginning to add NASA data to JS9. Right here, I have actually, let me go back to that. Let me go back to the Micro Observatory Lagoon. I don't know if you can see, in fact, if I, right here in that red area, there's a little V of dark, sorry, let me see if I zoom in, maybe you'll see it. There it is, a little V of dark shadow. And so in this Hubble image, that's the V of dark shadow. We've zoomed right into the center of the Micro Observatory image, and that's the Hubble image. But we can also look at an X-ray image of that same area. Looks very different, just like the image of the crab. And here's a Spitzer infrared telescope image of the same area where we see all that glowing dust. Again, Brandon, very happy. And the software will allow you to do the same thing and combine, even work with your own NASA data of different wavelengths. The Chandra website has a special set of images in which you can look at the different wavelengths and see a composite image. And the slides that we'll share with you have a whole, have the website to look up all these images. And then the final resource, actually 2 final resources. One is a series of videos called Universe Unplugged that our partners from the Spitzer Space Telescope at IPAC have created. And there is a movie called Electromagnetic Spectrum, the musical, which you really must listen to, but we don't have time to at the moment to get the full impact. But they are kind of fun, fun ways to look at different concepts in astrophysics. And in this one is sung about the electromagnetic spectrum. So those, I think, are the resources that I wanted to show you live. And the last resource that is coming up next year, possibly when some of you are implementing, is an online tool for looking not just at images, but at spectra, which Tim will talk about when he covers the whole electromagnetic spectrum. I think that's the resources that we kind of wanted to highlight for you. Tim, I think I'm going to stop sharing and let you do the sharing so that you can advance the slides yourself.
That sounds good to me. Let's see, share. And I probably want to share this one. Oh, come back. There we go. All right. So actually, before I touch on how we learn about the universe, Mary, can you pull up the poll results from earlier?
Yes.
Oh, I think we're getting our alert.
Our phones are alerting.
All right. So NASA puts telescope in space. Looks like majority of you put to get above the atmosphere, and a few people put in to get closer to the stars and the galaxies. While it is true that putting telescopes in space does get us closer to stars and galaxies, that's not why they are up there. The telescopes actually generally aren't all that much closer up there than they are on Earth. About Hubble, for example, is only about 400 miles or so up there. So that's the distance between where Mary and I are right now, between Baltimore and Boston about. So not that much of a change. But getting above the atmosphere is a big deal because the air will create a lot of distortions in our images, and the air will actually block some of the different types of light. And we'll see that as we're going along today. This one, I believe, only about 15% of the people who were polled on this originally got this correct. So that means there's a major misconception out there about why NASA does things like this. So this may be one of those things that you look for when you are figuring out how to address things. I will note as well, because it is colder in space, actually is appropriate for certain types of telescopes, if they're infrared telescopes like Spitzer or the upcoming James Webb, in addition to getting above the atmosphere. Both are important. But we'll go ahead and stop sharing this and move into how do we learn about the universe? So there are three basic ways that we have figured out on how to learn about the universe. And I'll start there on, I'm going to start on the right. That's a picture of cosmic rays coming to Earth, hitting the atmosphere, and leaving signals for us to detect. It is possible for actual matter to come here and for us to detect that. You could think of that as like, if a meteor was to come to Earth, we could learn some information about where it came from by examining it. We can also do this through really, really small particles. Cosmic rays are effectively just a couple of protons or neutrons in size at most. That is a fairly recent way that we've learned to learn about space. An even more recent way is pictured kind of on the left, gravity waves. You may have heard about LIGO. Last year's Nobel Prize had something to do with the detection of gravity waves in physics. LISA is an upcoming, not upcoming mission that is going to be out in space trying to learn more about gravity waves. Really exciting way to figure out what's going on. But the classic way we learn about what is beyond our Earth is through light. Most of NASA's missions deal with that, and that's what we're going to be talking about today, what light is and how that helps us learn about the universe. So what is light? Well, light is made up of a whole bunch of different colors. If you put light in through a prism, you'll see that it breaks the sunlight up into some different colors. We see red through blue, all the different colors of the rainbow. What that actually means, oh, there goes my emergency alert. I'm apparently a little slower than everybody else. Stop buzzing. All right. So as we go through all the colors and you get bluer and bluer, you're actually getting more energy, higher frequency, shorter wavelengths. You might remember that from high school, maybe not. I'll show a picture of what that looks like in the next thing. But what's really important here is there's actually no hard limit. Red through blue is what or red through purple is what we see. But some animals have a slightly shifted range. William Herschel actually set down a thermometer next to, he was measuring different colors of light to see if they had temperature differences, and set down the thermometer next to it outside of what he could see and found out, oh, this little area here next to the red was actually producing a lot more heat. And that's where we first came up with the idea of infrared light. So the electromagnetic spectrum, you've got a little bit of an image of it here. Objects across the universe will give off all different types of light. You can see this galaxy here giving off everything from radio on the left to gamma ray on the right. This one has higher and higher frequencies, more and more energy as you move to the right. Sometimes we flip them. Higher frequency means it doesn't actually go up and down, but that's how we represent it in images. But there's more of a pulse. The pulse happens more often, and that also means that the wavelength, the distance between those two peaks, gets a little bit shorter. And if you check out these slides afterwards, there's a link to this poster so that you can see what it looks like. And oh, there we go. Oh yes, Brandon and Mary are answering some of the questions in chat that people have had as well. So different types of light. Oops, going a little quick. Back up. There we go. Different types of light have different properties. And moving clockwise in here, if you were to hold up your hand actually stops visible light from getting through it. Visible light doesn't have the ability to go right through that. But something like an X-ray, X-ray is a color of light, and X-rays can pass through skin, but are stopped by bone for the most part, which is why taking an X-ray is so useful. You also have to be aware that things like X-rays and gamma rays can also mess with your DNA, move the sequences out and cause serious damage. That's why they cover you up when you're getting X-rays. UV light, ultraviolet light can as well, but it doesn't pass any further than your skin. That's what can result in sunburns and also possibly skin cancer if you are exposed to UV light out in the sunlight a lot. Microwaves, in the bottom right, are another color of light. One particular color within that microwave spectrum actually will get absorbed by water and cause it to vibrate and heat up very violently. And that's why we use microwaves in order to heat up our food. And radio waves have their own properties as well. That is actually light. It can pass through cars, it can pass through houses, which is how that radio signal gets to us, and then the radio receiver itself actually will turn that light into sound waves so that we can hear things. And Mary has popped up the next poll asking, sunlight transfers energy to the Earth's surface mostly in the form of one of these. Which one do you think? Go ahead and put your answers into that. I'll give you guys a moment. We've got a range of answers going on. All right. So thank you, Mary. So let's go ahead and get the results up there. Awesome. So looks like most people went with ultraviolet light, and then we had one person with visible, one person with microwaves, one with all of the above. Well, sunlight does light from the sun does emerge in all of the different colors: visible, microwave, ultraviolet, radio, and others. But if we're talking about what gets transferred to the Earth's surface, that is actually going to mostly be in the form of visible light. Our atmosphere does a pretty good job blocking a lot of other types of light. Radio will get through as well, but there's a lot more energy from the sun in the form of visible light. And that's actually why we see visible light, why it's visible. Our eyes have evolved to be able to pick up that most common type of energy. Oh, did we share results there? Make sure I click share so that you guys can all see that. So visible light is actually where most of that energy is coming through. So this picture I've got here is, you can see NASA telescopes are actually up there above the atmosphere where that energy still is getting to. And then as that sunlight tries to penetrate down further and further, it gets blocked by the atmosphere, and you can see which types are actually making it through. So because of this, NASA does have instruments that cover the whole electromagnetic spectrum so that we can learn about all of these different types. Integral, Fermi, Swift are all in the gamma ray, New Star, Chandra, XMM Newton are all collecting X-ray. And I should mention as well that some of these missions will actually spread out a little bit. For example, you can see Hubble down in the visible. Well, Hubble does reach into the ultraviolet light, and it does reach into the infrared just a little bit, but it's primarily there in visible light. And you can see some upcoming things too, like the James Webb Space Telescope, which has been big on the minds of astronomers across the world recently. When that launches, it's going to be looking into the infrared and going to be able to tell us things that we just cannot learn with visible light. All of these different types of light are going to tell us different sorts of information. We're going to talk a little bit about that because we learn different things. So our sun emits all of these different types of light, and we can see images of the sun imaged in different types of light. Now, I should mention that we've got them in different colors, and that's not the actual color there. In fact, I think only the first one in the middle row looks kind of yellow, at least to me, 4,500 angstroms. That is the only one of these pictures that comes across in visible light. We can see the photosphere, see some sunspots on there. All of these others are invisible to our eyes, so we're using instruments to collect that information, and then astronomers are coding that in a particular color just so we can make out what is there. Kim Arcand is going to be talking a little bit more later about representational colors and how we actually choose those and how there's actually a method to that. We're not just picking things completely out of a hat. I mean, honestly, we could make everything black and white, which is still the representational colors because we need to see it, but sometimes we'll put things in different colors so that we can differentiate at a glance. And we do this with more than just the sun as well. This is the Milky Way in different colors of light. You can see radio at the top, atomic hydrogen, which is just a really narrow band of light, the radio continuum, molecular hydrogen, infrared, mid-infrared, near-infrared, optical, X-ray, gamma ray, and all of these different things that are showing us different things about the universe. It's the same object pictured in different ways. So I mentioned I would get into what we actually see or what we actually learn from all of these different colors. So I'll touch on that briefly now. Gamma ray, we can see a picture of the entire sky here on the left in this kind of blue and reddish looking image. Gamma ray is really good at showing us pulsars, quasars, active galaxies, bursts such as supernovas, high energy collisions. This is actually a gamma ray map of the entire universe, the biggest thing that comes across is this big dark band and kind of bright around the edges going across the middle of it horizontally. And that's our Milky Way. That the center of that is a big source of gamma rays. And the next thing you might notice are these kind of big red bulges right above the middle of that, up and down. And those are the Fermi Bubbles. That's from the central supermassive black hole from our galaxy, and it's outpouring all of this energy from when it fed on lots of material in the past, and that's now emitting gamma rays that we're seeing. On the right, we can see X-ray. This is an image of Cassiopeia A, which is a supernova remnant. X-ray is really good at showing us neutron stars, some of the energy emitted from black holes, supernova remnants like this. Higher energy is going to be in blue in this picture, lower energy in other colors. And these different colors actually mean things. The blue here, excuse me, let's see. I think the red in this particular image is iron gas or plasma. The green is silicon and magnesium gas. The blue is titanium. So all of these different colors are telling us information about what happened after the supernova exploded and where all of these different elements went and how it's organized. And we can create some really cool things. And Kim has been doing a lot of 3D modeling with information from things like this, which is really, really fun to see. Ultraviolet is going to show us some of the hotter objects, not the hottest ones like X-ray and gamma, but hotter things like early and late stage stars will pop out in the UV. This is the Triangulum Galaxy, also known as M33. And we're mostly seeing a lot of young star formation. That's the bulk of what this light means when we look at ultraviolet. Hubble will collect a little bit of ultraviolet light. We don't really have, NASA doesn't really have too much up there in the ultraviolet range right now otherwise, but there are some proposed things coming, and there's some cool things that we can find. Ultraviolet, I think, is really good for finding the presence of oxygen, if I remember correctly. Visible light is what we are all familiar with. It's what we see. Most stars are going to peak in the visible light. This is the Eagle Nebula, and particularly the Pillars of Creation. It's one of the most famous Hubble images that is out there. Clouds of dust. This is clouds of dust with some stars forming inside them. And it's possible to figure out all sorts of information from visible light, figure out what different elements might be in there as well. And this is done through something known as spectroscopy. Mary alluded to that earlier. I'm going to try and make sure we talk about that a little bit today as well. Next up is infrared light. So I've got two pictures here. And infrared, all of these are really a broad range. Visible is the absolute narrowest band, and we define it as a range just because it happens to be what our eyes see. But all of these are covering huge swaths. And yes, Brandon, all of that beautiful space dust. On the left, we're seeing the Whirlpool Galaxy, M51, and all of that dust is warmed up by stars around it, and because it's warm, because it's got a temperature, it's emitting radiation, electromagnetic radiation, and it happens to be in the infrared area where most of this is. So we can see that dust really well. However, if you look at a different portion of the infrared spectrum, that infrared light will actually pass right through dust. It's transparent to it. So what you're seeing on the right are the stages of star development. It's 3 different images showing not the same object, because we don't have enough time to wait for a star to grow. But we're looking at 3 different spots. On the left, you've got a protostar. It's this tiny little red bubble. In the center, it's entering what's known as a yellow ball stage. And then on the right, you can see a bubble where this young star has kind of blown out this cavity around it, showing this nice red thing. It takes a couple of million years or something to do this, but this all is happening kind of enveloped in this cocoon of dust. And as that dust and gas collapses and creates a star, we get this bigger area blown out of it. And we're only able to see that if we use a particular wavelength of light that can pass through that dust and reach our telescopes. Next up, microwave. So you guys might have seen the picture on the left before. It's actually kind of a famous one within the realm of astronomy. This is the cosmic background radiation. This CMB is one of the biggest pieces of evidence in support of the Big Bang theory. It's actually a picture showing how how the heat of the universe is distributed. And it's that all of that heat as the universe has expanded has actually cooled down to about 3 degrees Kelvin, 3 degrees above absolute zero. I think that's what, negative 270 degrees Celsius. Brandon will correct me if I'm wrong. So it's real cold out there, and that's because the universe has been expanding, and this microwave information tells us a lot more about it. On the right, we have a really interesting image. This is taken in, the purple is actually visible light, but the orangish red color that you see there, it looks kind of like a little ghost, is radio. Radio is really good for learning about pulsars, quasars, cosmic background as well. This is the Boomerang Nebula here in particular. And that orange is cold molecular gas that we can visualize in radio. It's the cold, as far as I know, it is the coldest known object in the universe. It's actually even cooler than the cosmic background radiation. As that gas has been going through its wonderful physics, it has actually managed to cool down below the temperature of what everything else is around it. So there are, I should mention, a lot of misconceptions over the color of many of these images that we see. Lots of people think that, oh, this is what we're going to see if we were in space or if we got close to the object, which, I mean, most of these colors that we just looked at, we can't see with our naked eye at all, but it's not quite right. And other people will think they just made up those colors, which isn't quite right as well. And I'll save it for Kim Arcand to talk a little bit more about that. And Brandon's put a little bit of that pieces of evidence for the Big Bang in the chat if you want to take a look at that. So next up, I'm jumping back to Aster Pics, a little screenshot from that. Mary showed it a little bit earlier, but I do like this picture a lot. This is supernova 1987A. It's what is left over after a supernova went off in the year 1987. So a telescope is able to collect a lot more light over an extended period of time than our eyes can. It's like setting a camera out there with the shutter open for a long time. And when we do that, we're able to collect a lot more information than we can in that really, really quick blink. Oh, David, that was the Boomerang Nebula. So each color within this image does have some meaning and some scientific basis. So the red light that you're seeing in this particular image is radio, and that's coming from newly formed dust out there. The green light, which is kind of here around the edges, that is visible light, and it's forming what looks kind of like a string of pearls in there. The blue glow, that light is actually from X-ray light, which is coming from superheated gas. Both that string of pearls and that superheated gas are the result of the expanding supernova shock wave that's colliding with a ring of material that star outgassed gave off before it went supernova. And this is a really cool object because we've been able to watch this thing for a few decades. It's over 30 years old now, and Hubble was up there just a few years after it went off, and it's been able to take pictures and capture it as it went along, and Chandra very soon thereafter as well. Each of those different colors is telling something different, and looking at them overlaid over each other gives us an idea of the bigger story. So I'm going to jump to our next piece here. Oh yes, so images, this is just a little warning for you. Images of the EM spectrum, if you're looking around, you might see them flipped back and forth depending on who's made that image. Wavelength and frequency and energy are all directly relatable to each other. They're different ways of talking about the same thing. The wavelength numbers will go up in one direction as the frequency goes down, or the frequency will go up as the wavelength goes down. So depending on what type of astronomer you're talking to, they might put their pictures in different ways. For example, at the top, we've got gamma ray on the left and we've got radio on the right, and the wavelengths are going up as we go to the right, which means that this one was probably done by someone working in the infrared or the radio or maybe the visible, because people like their numbers to get bigger as they go to the right. On the bottom, you'll notice the infrared on the left and the X-ray and the gamma ray on the right. And that's because, well, this one was done by some X-ray folks who work with things in energy, which matches up really well with frequency. So they want those numbers to be going up as they're going to the right. Yeah, and Brandon's writing that out. Infrared make the wavelength go up as you go to the right. X-ray make the frequency or the energy go up as you go to the right. So just check which way is which as you are looking at these pictures, and don't be confused. It really doesn't matter which direction you're going in, but that could be confusing if you weren't aware that it happens. All right, I've got just a few moments here to finish up with the measuring the spectrum before we turn it over. So if you were to look at a particular spot of light and split it apart with something like a prism, you'd be able to see variations in the different types of light, the amount of light that's coming out there. Sometimes those variations are really big. So for example, if we look at the sun, we get a lot more visible light than we get radio light, just because of the temperature of the sun. Sometimes we're looking at a really small thing. So if you look at this little rainbow here, so we've got light from this galaxy coming through a prism. It's being split apart into its different types of light, and you'll notice in that spectrum of light, in that rainbow, there are some dark lines, and that's just because there's just a little bit less light at those particular spots. So if you use a computer to measure how bright those spots are, you can turn that into a graph, kind of like what we have below. Now this graph is actually looking in the infrared light, but you can see there are some big dips, and those dips kind of correlate with where some black bars would be if you were to look at it with your eyes. And if you happen to look at the patterns, you can figure out that the presence of certain chemicals might create dips. So for example, in this graph we have here, acetylene is creating a dip here on the left. In the middle, we've got a smaller dip as the result of hydrogen cyanide. And over on the right, we've got a dip as the result of carbon dioxide. So this is looking at some molecules that are around a star, IRS 46. And looking through that, you're able to figure out that there is some, oh, my monitor just turned off on me. There we go. Okay, you're able to tell that there is a presence of particular molecules, which is a really cool thing. We can look at other stars, we can look at where planets are, and we can figure out what's in there by breaking up the light and looking in particular ways. We can do other things with this as well. So we can measure the redshift of things. So say you know that there is a particular pattern when you look out at certain objects, that in this general area of light, there are these couple of lines that always match up together. It's a signature or a fingerprint. But if you look at where that pattern is, you might find that it's moved a little bit relatively, and the pattern is slightly the wrong spot. It's a little bit too far towards the red, and that might actually happen because galaxies are moving away from us. Because the space between us and the galaxy is getting bigger, the wavelength of that emitted light actually gets redder, and that's due to motions of the galaxies through space, and that's kind of like the Doppler effect. If you listen to an ambulance that's driving by, you hear a really high pitch at first, and as it goes past, it starts to get lower, and that's because those wavelengths are actually spreading out. It's also possible for redshift to happen due to the expansion of space. As the universe gets bigger, those wavelengths stretch out and become bigger, and we can actually use that to figure out how far away the source of light is. Oh, it's all very confusing at the first time you hear it, so you're going to feel overwhelmed. I'm sorry. But we'll come back to this point, and we'll talk about it a little bit more as we go through the series and give you a little bit more of a sense of it. But the big thing to take away is that a lot of the science that we do is through spectra, by looking at the light in a very detailed level, figuring out how much light in these different at these different types of light. We're not necessarily looking at images all the time. We see images because of the pretty things, but these spectra are really important. And I know that our methods of communicating about spectra aren't as good as using images all the time. They're very confusing that when you first hear about them, as you're probably dealing with right now. So there's a barrier in communication why these wiggly little lines are important. So if you have some ideas about ways to talk about them, please put them up in the community of practice. Let us know what's there. Also, consider making a project about that, because we're definitely looking for more like that. And thank you, Brandon, for clarifying some of the things I've been talking about there. But with that, I'm going to turn it over to our subject matter expert for today, Kimberly Arcand. And Kim, you're there, right?
I am. Can you hear me okay?
Yes, we can. I'm going to stop sharing my screen
Great.
so that you can pull up what you've got on your own.
Great. Okay. Can everyone see my screen?
Yes, we can see it. There you go. Now you're in presenter view even.
Great.
So I guess I'll jump right in. Hi, everybody. My name is Kim, and I work for the Chandra Observatory, as I've heard mentioned quite a few times, which always makes me happy. Chandra was launched back in July of 1999. So we're actually about to hit our 20th anniversary next year, and I'm super excited about that. So one of the great things about Chandra is that, as Tim and everybody else kind of mentioned already, it's an X-ray telescope, and it has to go above our atmosphere because our atmosphere has all these superpowers, and one of its superpowers is to protect us from X radiation. So Chandra goes above it about a third of the way to the moon in order to get a really clear picture of the X-ray universe. And some of the things I'll be showing you are just a few of my favorite ways to talk about the electromagnetic spectrum, and also one of my absolute favorite data sets to work with. Chandra, by the way, is about the size of a school bus. It has amazing resolution. It's like the ability to read a stop sign about 12 miles away. So it's a really sophisticated piece of equipment. As you can see here, this has already been repeated, so I don't really have to say much to it, but if you look down at the scale, you'll see that gamma is on the left and radio is on the right. So this is just another example of sometimes the electromagnetic spectrum runs one way and sometimes it runs another. This is just one I grabbed from our website, and it doesn't really matter to me which way it goes, but I do tend to like X-ray on the right. So when I'm talking about the electromagnetic spectrum with classes or with people at a museum, I usually like to start off with analogy of some kind. And I think you've heard some really good introductory material already, so hopefully this just adds a few sort of tools in your back pocket. One of the analogies I like to use is the idea of why we need to use different kinds of light to study the universe. And if you're looking at my screen now, and if you're familiar at all with baseball or softball, you might recognize that this is the third base foul line of the baseball field. And the reason I show this is because I like to have people imagine what it would be like to watch a baseball or softball game if this was the only part of the field that you could see. It'd be really hard to understand the rules of the game. It'd be really hard to know what the players are doing, what's going on. And so just like that, in astronomy, if we could only see the type of light that our eyes can detect, which is optical, or if we could only see any one single kind of light at all, truly, it'd be very hard to figure out what's going on in the universe. So by being able to have the entire screen, to be able to see the entire baseball field, by being able to see the entire universe in many different kinds of light, it just gives you a lot more information to work with. And just like in baseball, there are going to be mysteries still, at least I know there are for me, but the idea is that it gets you a little bit closer to figuring things out. Of course, the catch in astronomy is that every time you figure out the answer to like one question, about 10 more questions pop up, which is probably why I like working in this field so much. It appeals to me. Another analogy I use sometimes if you're not feeling sporty is a music analogy. For anybody here who's into music, or particularly the piano, if, again, you want to liken the electromagnetic spectrum to the keys on a piano, and if you could only see with the type of light that our eyes can detect, it'd be like being able to only play your favorite pace of music with middle C and maybe a couple keys around it. And for any of you who play the piano, or any instrument really, if you only have access to a few keys, it's going to sound kind of dull. Your favorite symphony is going to be quite boring. But as soon as you have access to the entire keyboard, you have access to that greater symphony of music that I think we're all much happier with. So in astronomy, again, when we're looking at different kinds of objects, we have different kinds of light that we can choose to work with. We're looking right now at a supernova remnant called Cassiopeia A, and this supernova remnant is, of course, when a star maybe about 10, 15 times the size of our own sun got old, it ran out of fuel, collapsed, and then exploded all over the place. We're looking at this beautiful image from the Hubble Space Telescope showing delicate filamentary structure around the 10,000 degree mark. We can look at that same exact field of view from the Chandra Observatory, and it looks completely different. And the beauty of this is when you put your data sets together and you can explore the universe by using more than just one kind of light. It really both gives you more information to work with, and also visually it helps you set the context for what type of object it is that you're looking at. Because one of the things working with X-ray astronomy is when you're looking at data sets like this and you don't have a lot of frame of reference for what exactly it is, sometimes people might think it's something that belongs under a microscope or a medical image or what have you. So for us, being able to combine with other types of light not only gives us more science to talk about, but also helps really set the context for people who are looking at these images. So again, as we talked about already today, these images of the universe are not giant cosmic selfies, right? That'd be kind of fun, I guess, but the whole process of creating an image, I think, is much more interesting than that. And the idea is that these images are a true translation of information. So images of our universe start looking out a little bit more like this, or perhaps a little bit more raw, like the one on the lower right, but really they start out looking like this. And this is just binary code. Binary code is essentially a system of ones and zeros, which is ons and offs. Our electrical equipment uses the systems of ons and offs to talk to each other. So we use binary code to talk to our laptops, to talk to our phones, and we use it to talk to different kinds of spacecraft. So when we have an object like supernova remnant Cassiopeia A, that light has been traveling from Cassiopeia for a long time. That information is recorded on the detectors of the telescope. In this case, we're looking at Chandra. That information is then packaged up in the form of ones and zeros and sent down to Earth before it makes its way to somebody's laptop, perhaps mine, perhaps somebody else in my group. So after we get that information, we have to use some data software to essentially process it to create the visual representation of the object. We actually first start out with a table of information that records each X and Y low coordinate, and then also the energy and the time for each photon, each packet of energy that was recorded during the observation. And we use more software to then translate it into a visual representation like you're looking at here. One of the final steps that we do typically apply is the idea of adding color, because again, as already mentioned, this is a type of light that we can't detect with our eyes. So there is no inherent color truly in it that we would be able to see. If we zoomed out in our spacecraft to see Cassiopeia A, it wouldn't look like this at all because we can't see X-ray light, period. And it wouldn't even really look like the Hubble image that I showed previously, because Hubble magnifies and amplifies light so that we can see it a lot better. So when we're looking to take our image and create some sort of color composite version, there are a couple different ways we can do that. We can slice up our image by energy cut, essentially. So we can take the lowest energy X-rays and apply it with red. We can take the medium energy X-rays and apply it with green, and take the highest energy X-rays and apply it with blue. And you can see that it creates this three-color composite that adds to the information quotient of the image. Because in looking at a data set like this, the scientist is going to know from looking at the spectral information, the sort of DNA fingerprint of what's going on. When you're looking at it as a non-expert particularly, you have a lot less information to work with. So by color coding it, it's just like color coding something on the nightly news for, say, the meteorological forecast, right? If you're color coding a weather map by temperature, it automatically gives the viewer something to be able to take away really quickly. He or she will know, you know, where the warmer patches of the day are going to be in their state, for example. So we can do something similar with our data, whether it's X-ray data or something else. By being able to color code it by energy, for example, we're seeing here in Cassiopeia A that this high energy ring of particles around the external region, that's the acceleration of the shock. So we immediately know that there's high energy material kind of around that remnant like that. It gives you a quick visual cue. But we can also process images by other methods. We can detect essentially the chemical emission, the emission from chemical elements in that supernova remnant as well. And in this case, we've colored the silicon red, the sulfur yellow, the calcium green, the iron purple, and then the blast wave in bright blue to get this version, which is what I showed earlier, the first version that I showed in the PowerPoint. And again, that just adds the information quotient of the image. So you can see a little bit more quickly where there are specific pockets of, say, iron, right? You can see very clearly where some of the calcium is residing. And that sort of information is actually really useful to astronomers. Sometimes when these stars explode, they kind of turn themselves inside out. So when you're mapping that kind of information into an image, you just get a much faster visual reference to be able to see it. When you're working with telescopes like Chandra or Hubble or the Spitzer Space Telescope, you know, they have been around for a long time. So you can also look at their data and see it track across time. So you're looking here at a movie of Cassiopeia changing. I like to show representations like this because it helps get the point across that objects are dynamic and ever-changing. And you can see we kept the similar color code that I mentioned before, where it's cut by energy. We can also use color in a very different way. I think somebody mentioned it previously, but we've been working on creating three-dimensional maps of objects like Cassiopeia. In this case, the color is slightly different. We've got pockets of green, which is the iron. We've got the fiducial jets colored in purple. We've got some optical data in yellow, etc. So in this case, the colors are slightly different because of what kind of software we're using, but it still adds value to the overall object. We've also tried things like 3D printing them, which the first types of 3D prints we got were a single color, but then we started working and experimenting to create multicolor 3D prints as well. So again, it's being able to show that color information in a different format. And most recently, as also mentioned, we've been trying to work in virtual reality. So using things like Oculus Rift, Oculus Go, and Google Cardboard. Again, by applying color, you can walk inside a dead star and then understand where the pockets of iron are, where the pockets of calcium are, where the pockets of argon are. So that's pretty much the gist of it. Again, all of those types of representations that I showed you, they all came from a set of ones and zeros. Granted, a really, really large set, like millions and millions and millions and millions of lines of ones and zeros to form the visual representation of the images. And if you're interested in any of the things that I showed, I'm sure they'll have the URLs up on the window too, but here are a few URLs too.
Thank you very much, Kim. Do any of you, what sorts of questions do you folks have for her before we wrap up today? You can speak them out loud or put them in the chat.
Yeah. If you want to unmute yourself, you can use the participants tab. If it's easier for you to just shout out your question to Kim.
Kim, what can the Shandra telescope tell us about the very earliest objects in the universe?
Well, Chandra looks at light that's actually really old. I have an interesting stat about that, actually. Hold on, let me look it up. I think, so Chandra is looking at things that are both really huge, such as like clusters of galaxies, and also incredibly, incredibly old. Like some of the light from quasars, for example, has been traveling through space for 10 billion years or more. Chandra has been able to look at the deep fields that you might be familiar with already, like the Hubble deep field, some of the ultra deep fields, and frontiers fields. To be able to understand light from the early universe. And a lot of what Chandra looks at is about black holes. Because there's not quite as many X-ray photons in the universe as there are, say, optical photons. So things that are creating X-ray photons are things like black holes, quasars, colliding galaxies, exploding stars. It sounds all really violent. But there's also, you know, X-rays coming from quieter things like the moon. So anyways, I hope that answers your question.
Thank you.
Sure.
have a question, Kim. When one of your slide about creating an image that's based on the actual elements emitting the light. So I know Chandra has made some discoveries, like you've got an exploding star there. And so what is it that seeing the placement of those elements in the supernova remnant what story does that tell?
Well, actually, one of the stories that we first understood with this was about the star turning itself inside out. That actually was a new discovery and a new surprise. So when we first started looking at the dispersal of some of these elements, for example, and you could see that iron was often in some of them on the outer perimeter versus where you would think it would be, which would be closer to the inside. Because as the star is aging, right, that iron is growing in the core. And so you would think, at least I thought, when a star explodes, that the material, you know, the iron, which is close in that core, would be closer to the central part of the explosion. But that wasn't the case. And that was one of the things that led some astronomers to understand that stars like Cassiopeia literally turn themselves inside out when they explode. So I think things like that are really interesting because you know, it's that classic stardust reference, you know, when you're thinking about why we care about things like supernova remnants and the fact that these elements that are created are the same elements that we have residing in us and in all the things around us, the iron in our blood and the calcium in our bones. It's really interesting to think how that process of dispersion happens. Or at least it is to me.
Me too. Thanks.
Mm.
All right, we seem to have run out of time here. So if you do have more questions, please put them online in the Moodle on the community of practice, and we'll make sure we can get those answered for you. Please remember, 2 weeks from today, October 17th, we're going to be moving on to Looking Out is Looking Back in Time. We talked about how we've been looking at these very far away things. Well, they're also really, really old. And next steps, please pop online, contribute to the weekly discussion topic, ask any questions you have about the application for the mini funds, and again, show up for our next webinar. But thank you everyone for coming today. It's always great to talk to you guys and listen to your questions, and I look forward to doing it again.
Thank you so much, Kim, for your great presentation.
Yes,
really.
Absolutely.
Yes, thank you.
Thanks, bye.
All right. So see you all online and on the 17th.